Hi, everybody. Our next speaker is Dr. Beatriz Molero. Dr. Beatriz Molero is a dynamic entrepreneur and scientist, driven by curiosity and passion for solving meaningful problems in the nexus of technology, business, and energy transition. She's the co-founder, CTO, and director of the company SeeO2 Energy in Calgary, Canada, and she was recently awarded the Alberta Government Green STEM Fellowship to support in the business and technology development of her company. Dr. Molero received her BSc and MSc in chemistry from Complutense University of Madrid. She moved to Calgary in 2011 when she received the prestigious award Transatlantic Science Student Exchange Program. In 2012, she accepted a position as a PhD candidate in Professor Viola Beer's group at the University of Calgary, where she spent 5 years as a teaching and research assistant. For the past 9 years, she has been working on helping carbon dioxide becoming a profitable asset rather than a liability for the planet. She spent 6 years developing high-performance and novel electrolysis system, and the last 3 years leading SeeO2 Energy to commercialize the platform technology. Some of Dr. Molero's selected achievements include the 2019 Federal MITAC Environmental Entrepreneur Award, the Skinner Prize by the Royal Society of Chemistry, the Alberta Innovate Technology Futures Doctoral Scholarship, and the ACE High International Doctoral Scholarship. She also received a professional development grant to travel to MIT in Boston to work on a collaborative project. Dr. Molero has been involved in several boards and committees over the years, with some examples being the president of the Electrochemical Society Calgary Student Chapter from 2016 to 2018. Beatriz, thank you for coming.
Thank you, Jesus. Thank you for the kind introduction, and thank you for the invitation as well. It's always a pleasure to be virtually at home. And I would like to thank Professor Alario as well for dedicating his work to Professor Moran. And on that note, I would like to invite everyone to submit original work to a memorial issue on Professor Emilio Moran's name. It is open until the end of December 2021. Okay, so today the structure of the talk that I'll be giving, it's a little different than the other speakers. And so I'll have 50% of the talk dedicated to the work that I perform on the academic level at the university research, and the other 50% of my talk would be on the work that I perform as leading our company, SeeO2 Energy. So on that note, I couldn't decide which title slide to make, so I have both. This is the exact same information with the company logo and the university templates. So I will start chronologically with the university research work. So as we know, there's a worldwide increase in fossil fuel combustion, and it has led to high concentrations of CO2 in the atmosphere, which leads to climate change concerns. I like to use this drawing from Professor Abruña, Energy in the Age of Sustainability paper, which is very adequate to the workshop today. And I mean, you can interpret this image in different ways, but I like to think about it as the innovation being a key part of the energy transition, and innovation being, as a scientist and as chemists, playing a key role in that transition, or we like to think that. And here we can see renewable energy, solar and wind represented, and energy storage in this bottle, and as a key part of this transition to really power the planet and leave it somewhat in good shape for the next generations. Okay, so one of the key points in that energy transition is energy storage, as I mentioned. So energy storage, there's kinds of renewable energy that are intermittent, such as solar and wind. So here what I'm showing is a graph where the red line represents the energy demand. So that's a fixed amount that we need in a certain day or a year. And the yellow is the solar, green is wind. So there are times where the combination of both renewable energies does not meet the demand, does not get to the red minimum. But there are times where there is a lot of wind and a lot of sun, and we exceed that demand, that requisite. So at these times, this energy is simply wasted. We're just not using it. Whereas there's times out here that we would need extra energy. So that's where storage, represented in purple, plays a key role in this energy transition. So we have heard in this workshop different other methods and other ways to store energy, and we will probably need all of these solutions in the future, but I will focus on what's called power to fuels with electrolyzers. So as an overall concept to use electrolyzers in this, to solve this issue, we would be using excess renewable energy, such as solar and wind, at those times where it's higher than the demand, and we'll be using it to power the electrolyzers. That way we can convert things like water and CO2 into gases such as hydrogen and CO, and these gases can be stored. They can be stored either in gas cylinders or underground, and you could actually use them at a later time, at those times where we actually need some extra energy because we don't need the demand. We can use those gases that are stored to run the fuel cells and create clean power. So this is an indirect way to store that excess energy in forms of chemicals and fuels. So there's many different kinds of fuel cells, and I'm not going to get into all of this. I would like to just say that there's different kinds of them, and they're classified. Their names really refer to the materials of the electrolytes, and they operate at different temperatures, and because of that, they can be used for many different applications. If you are familiar with hydrogen or fuel cell cars, those will be PEM fuel cells down here, and I will be focusing on reversible solid oxide fuel cells, which are mostly made from ceramic materials. So what is a solid oxide cell? These cells have three main components: two porous electrodes and a separator and a dense separator or an electrolyte in between. The porous electrodes allow the gas to come in and come out, and that's where the electrocatalyst is, and that's where the electrochemical reactions take place. The dense separator, it prevents the gases from mixing, and that's where the oxygen and ions travel in between electrodes. So reversible solid oxide fuel cells, they are single devices that can be used as electrolyzers, so to store electricity, or as fuel cells, the same device. So in the fuel cell mode, here, the SOFC mode, these reactions are spontaneous and they're exothermic. And in this mode, gases such as carbon monoxide and hydrogen are the inputs for the fuel electrode and oxygen to the oxygen electrode. In this field, we don't like to call them cathodes and anodes because the cathode becomes the anode in the electrolysis mode and vice versa. So we like to call them the fuel electrode and the oxygen electrode to avoid confusion. So in this mode, the electrons that are generated are output into the external electrical circuits, and it creates clean power. Now, the same device can be run in reverse. And in this case, now the electrochemical reactions become non-spontaneous and endothermic. So now we need power to run these devices. And that's where we take that power for the excess renewable energy. And here, the inputs for the fuel electrode are carbon dioxide and or water. And at the oxygen electrode, we produce pure oxygen. So traditionally, there's been quite a bit of research historically on the SOFCs. There's quite a bit of research done on these materials and the components for SOFCs. However, for high temperature electrolysis, or SOECs, it's a fairly relatively newer field, so there's less research that was performed there. And conventionally, lots of people took the materials that were designed for SOFCs and simply ran them in reverse. But there are problems with that. As you can see, the atmospheres and the requirements for designing these materials are quite different. So, for example, when using conventional electrodes to run them in reverse, several problems show up. Things like delaminating from the electrolyte. So that's physically delaminating the two solids during electrolysis. They can react and create insulating secondary phases. Or there's actually low ionic conductivity, and that makes the reaction really limited to what's called the triple phase boundary. And the triple phase boundary is this intersection here between the electrolyte and where the porous electrode meets, and that's where the electrochemical reaction is limited to. So because of that, people start using composites to try and meet those conditions and to increase that triple phase boundary length. So we started looking into what are called mixed ionic and electronic conductors. The reason being is, as I mentioned, with pure electronic and conventional materials, the reactions are limited to these TPBs down here. But when you have a mixed ionic electronic material, now you're extending the reaction, the surface where the reaction can take place for the entire surface of the catalyst. So you're really extending that reaction area. So we started working on different composites and compounds, and we actually landed in this mixed conductors. There's strontium and calcium rich chromium ferrites, and the goal here was to develop materials that could be used for both the fuel electrode and the oxygen electrode. Traditionally, you would use one composition for the fuel electrode and one composition for the oxygen electrode. So here we wanted to use in a symmetrical configuration the same material, so they really need to be stable in a wide range of PO2s. So one of the first things that we need to find out is the conductivity, because they need to be good candidates to conduct in all of the atmospheres as fuel and oxygen electrode. Secondly, we need to find out the chemical stability in SeeO2 and SeeO, which is not trivial. There's a lot of these perovskites that have secondary phases or decompose in reducing atmospheres. And also the thermal expansion coefficient of these materials is really important because they really need to match, the electro material needs to really match the electrolyte material TC. Otherwise, it could also physically delaminate and stop working. So these materials were synthesized by regular combustion synthesis, and then we would fabricate ourselves, as I mentioned, in the symmetrical configuration by screen printing the electrodes on both sides. The way we perform our testing, there's different configurations, but here I'm sure a 3-electrode half-cell configuration where we have the working and the counter electrodes. Again, we have the same material and reference electrodes, and this is just a picture of the setup that we were using on those devices. So one of the main techniques that were used to characterize this electrocatalyst is electrochemical impedance spectroscopy. And here one of the main parameters that we look at is the RS, or the ohmic resistance, which is the series resistance, which is the concentration from the ohmic resistance from the electrolyte and the contact wires, but also the polarization resistance, or RP, which is inversely proportional to the reaction rate. By fitting all of these results with equivalent circuits, we can extract many parameters such as resistance, capacitance, frequency ranges, and these values are really important to help us really understand the physical processes in these materials and then at the reaction mechanism levels. Now, so here I'm just showing a quick example of how we would do something like that. So here I'm showing the oxygen reduction and oxygen evolution reactions. So those are the two reactions that occur at the oxygen electrode in the SOFC and the SOEC mode. So when you perform electrochemical impedance spectroscopy at what we call the open circuit potential, or the black curve, you are measuring the reactions at equilibrium here in the middle. This is a CV, or a cyclic voltammetry, a different technique, but they're related. When you apply a negative potential, in this case, you are pushing the reaction to the SOFC mode, or the oxygen reduction side, to this branch out here. And you can see it here in the impedance curve as well. And when you apply a positive voltage, then you are pushing the reactions out here into the electrolysis mode, or the SOEC mode, and you can see it as well in the red curve. So that is how we use these techniques and different voltages to really push the reactions to understand the mechanisms of the different reactions involved. So in a nutshell, I won't get much into this, but we use this fittings and these results to try and understand the reactions at the mechanisms levels. So here shows a simple breakdown of what happens at this reaction, the reduction reaction. And we use this results to understand what happens, which is the rate determining step, and what happens at which step. So as an example, we can use it to identify, for example, at low frequencies, we know these are surface processes. So the surface of the catalyst, so that would be the solid gas interface. Or we could use it, we also know that at high frequencies are processes that happen at this interfacial process or solid interfaces. So it's quite a powerful technique to understand these reactions. So just to give you a quick visual representation of how these devices look after post-mortem or after being tested, you can see these porous electrodes and this thick electrolyte here. And you can also visually see when I mentioned the problem of the physical delamination, it actually, you can see it really well in this SEM here, they actually physically delaminate and then they would stop working. So we did a lot of work to try to avoid that, and the compositions that we choose to not delaminate. And here is some proof of that actually was performed in collaboration with Dr. Avila at the Universidad Complutense of Madrid. And you can clearly see that we don't see that this is after hundreds of testing. You can clearly see that delamination problem is not there. You can see it on the atomic level beautifully. You can also see the mappings out here of these ions. So one of the last things I would show in this first part of the presentation on the fundamental research is the work that we perform to really try to fabricate these devices entirely by microwave methods. And as a lot of you might know, that was a big line of research for Professor Moran and Dr. Prado as well. So that was a work performing collaboration with them. So the idea here would be to completely fabricate these devices from powders into the fully electrochemical cells entirely by microwaves. So that includes the synthesis of the catalyst, the electrolyte, the sintering of the electrolyte, the sintering of the electrodes onto the electrolytes, and the actual microwave, the cell sintering completely. And so just really quickly, I will mention that one of the reasons to start this idea was because at the end of the day, into looking into commercial applications or industrial applications, what's really interesting is that you decrease that synthesis time by quite a bit, and the power consumption as well. So with that, I would just like to thank the Burrs group. So here's Professor Burrs out here with her research group in the summer and in the winter, and all of our collaborators and past and present members of both the Burrs and the Tangadrai groups. And here is Dr. Ada and myself are over here as well. So my work and his research, we both took that research and try to start this exciting adventure of scaling up and starting this spin-off company with SeeO2 Energy. So this is a nice segue into talking a bit more about what the company or SeeO2 Energy is today. But before I get there, this is a nice transition into the scale-up work or all of the work that goes involved from fundamental university research level into scaling up into industrially relevant quantities. And I think if you have a visual representation of these cells, the black part is the electrodes and the white is the electrolyte. We like to compare it with Oreo cookies just because they're the colors and they're symmetrical. And as I mentioned, that symmetrical configuration is really important to us. I think one of the speakers yesterday mentioned that scaling up, even for the powder synthesis, from milligrams to grams to industrially relevant quantities, that already it's a big challenge from fundamental research into big scale-up work. Never mind the actual cells and the actual ceramics. This is just an animation showing you how the processes work. And that's more of a visual representation of the scale-up work over the years. So the device that I'm holding, that size, or that coin size, is the full devices that we worked on at the university level. So all of the research that I've showed up until now was performed on this size of devices, and this is these are the university labs. Now, the cell that Dr. Addo is holding in this picture, this is a 10 by 10 cell, and these are the scale-up cells that will be used in commercially ready prototypes and shipments. So he's now in our labs. This is our company lab at the back, and it's about two and a half years difference in between these two pictures. And just to put it in perspective, the size that Dr. Addo is holding, that is the building block to make larger units, and you would put several of them in parallel to make bigger devices. And so, just to get a bit more into that, the active area for the devices that we use at the university level, it was 1 centimeter squared. And we scaled up by 100x to 100 centimeter electrode cells. Now, in this picture may look really simple, but there's quite a bit of steps in between. There's 2 by 2s and 3 by 3s and 5 by 5s and lots of trial and errors. And then when you get to this size, then you need to build the stacks, and then you put several of these cells in parallel to make bigger units, as this animation is showing up here. So we've then done shorter stacks, 1 cell, 2 cells, 5 cell stacks, 15 cell stacks, until we developed a fully developed benchtop prototype that converts 4 tons of SeeO2 per year. Okay, so that concludes that transition sort of presentation from the university level into what the company is doing. So I would now talk a bit more about the spin-off company, SeeO2 Energy. So as I mentioned, this is a spin-off company out of the University of Calgary. We're based in Calgary, Alberta, Canada. And quick highlights, we are a clean tech company, and we convert greenhouse gas emissions into high-value fuels and chemicals in a net negative carbon process. And as few quick highlights of our company, since we co-founded the company in 2018, we have accelerated those prototypes by more than 200x, which, as I just mentioned, it may seem simple, but it's actually quite a big achievement. We have 3 pilot customers, industrially relevant, and I will discuss them a bit later. We have 4 patents, 2 issued and 2 pending. We have raised 1.3 million for the development of this technology, and we've won a few awards in this field as well. Our target customers are metal processing industries, oil and gas, utilities, green plastics, and specialty chemical industries. So to put it in perspective, why this becomes so important, as a company, we're focusing more on the electrolysis side. I'll get to that of these devices. But in general, there is a global demand for the industrial gases that we produce. So that is carbon monoxide, syngas, hydrogen, and oxygen. And that global demand will continue to increase. And traditionally, these industrial chemicals are made from fossil sources. And we know that at the same time, there's a global increase in SeeO2 emissions, and it will continue to increase. So why not? We've learned really well how to recycle our metals, our plastics, our glass. So why not recycle our SeeO2 emissions and use that to produce these fuels and chemicals in a more sustainable way? So that's what we do at SeeO2 Energy. We provide our customers with a robust solution to turn their emissions into assets. So our value proposition is to be on site at an industrial location and take the emissions before they're released to the atmosphere, run them through the devices, and convert them into these high-value fuels and chemicals. Now these products will be recirculated into the industrial processes, closing the carbon loop. So this technology, as I already mentioned in this talk, and you have all the technical info, these are high temperature electrolysis. They're built with ceramics, and to scale up, you put several in parallel. This is just an animation showing how the technology works. If the animate, there you go. how the technology works in a more visual way. And our technology can be applied in different applications because we have the ability to produce different gases depending on the input. The technology is identical. The only thing that will change to produce a particular product is the input. So we can make all of these products depending on the inputs. Now, electricity and heat are constant inputs, as you know, and I have explained in what this non-spontaneous reaction and endothermic reactions need. So to produce just hydrogen, which, as you know, is widely used in different industries, then the input will be only steam. To produce just carbon monoxide, which is widely used in petrochemicals, green plastics, metal processing, electronics, and so on, then the input will be only carbon dioxide. And to produce syngas, which is a combination of carbon monoxide and hydrogen and is widely used in lots of industries, then we would input carbon dioxide and steam. And the very different thing about this technology is that we can tweak the ratio from carbon dioxide to steam to produce different ratios of CO and hydrogen, which is what's needed at the industrial level to be able to have flexibility in the ratios of CO and hydrogen. In all of these modes, pure oxygen is always a byproduct in a separate chamber. So we could also widely use that pure oxygen. So one of the things that's really important to us is the life cycle assessment of the CO2. So here we're comparing there's no units in here. Here we're comparing the emissions for 1 kilogram of syngas produced, comparing incumbent technologies, in this case SMR or steam methane reforming, low temperature electrolyzers and high temperature electrolyzers. So as you can see, there's quite a big difference in not only, we actually can consume quite a bit more of CO2. And the major reason for that is that because we operate at high temperatures, thermodynamically we're favored. These reactions are a lot more efficient. The electrical input required for the technology is about 30% less than low temperature electrolyzers. So that really plays a role in the life cycle assessment of the carbon dioxide. So we have 3 industrial commitments as of today to field demonstrate the technology. ATCO is a utility company here in Canada, and they're also a minority shareholder in the company. And they're interested in the syngas because they need to replace 10% of their natural gas production by renewable natural gas. So they will take our clean syngas and then convert it into renewable natural gas. And we're going to be piloting with them to produce syngas, but also hydrogen, as they recently got interested into using hydrogen inside their processes. We also have Equinor and TCM Mongstad in Norway. We were in Norway for 4 months in 2019 as part of Texas Energy, and Technology Center Mongstad is a center that belongs to Shell, Total, and Equinor, and they capture CO2, so we would be testing their captured CO2. And ArcelorMittal, it's a metal processing giant, and they're interested in carbon monoxide, but also syngas, and they will transition into hydrogen as well. In the metal industry, they need these reducing gases in their metal processing process. So as part of those pilots, we will be piloting in one of their plants in north of Spain, in Avilés, in their gas lab, to test industrially relevant sizes of the technology out there. The project it's predicted to be on site by the end of the year, depending on how the world looks by then and travel restrictions and other restrictions. So in terms of our timeline, as I mentioned, we are now in what we call the pre-commercial phase. So we're taking those benchtop prototypes into the field, and we're testing with our industrial partners, the 3 that I just mentioned. And then we would scale up into commercial products. The way to scale up is simply putting more of these modules together or boxes together to make bigger units. Our commercial units will convert 400, that number is wrong, 4,400 tons a year per unit of the commercial units. And then we can get to large-scale adoption of the technology. So we have quite a few partners that have already talked about ArcelorMittal in Spain, ATCO in Canada, TCM in Norway, and we also have Nexaris in the US. In the last 3 years, we've got quite a bit of industrial support a couple of grants here in Canada, international grants, and international incubators and accelerators to accelerated technology. We have a multidisciplinary team from chemists and engineers and long-term professionals in the energy sector, past CEOs from very well-known companies. We are building a team that has the experience to take this technology into the field. We are at the intersection of clean tech and hard tech, and that is a really hard business to be on. And so we're really building a team that has the necessary expertise to make this successful. And overall, we have more than 100 years of experience together in commercializing technologies, over 50 plus in CO2 conversion technologies, and over 50 plus in materials development for clean energy. We've won a few awards since we incorporated the company in 2018. We're particularly proud of the World Energy Council Top 100 Startups in the energy transition in 2019. We recently got a Eureka label for our project with ArcelorMittal in Spain. We got an investment from Third Derivative, which is a climate tech initiative in the US from the Rocky Mountain Institute, and it's selected from hundreds of climate tech startups across the world. And also we were part of Texas Energy Accelerator in Equinor in 2019. So with that, I'd like to conclude my talk, and I would just say that I can welcome any questions. And as Jesus didn't allow me to put any more of my pictures of polar bears, I'll just leave you with the one last at the end. Thank you.
So thank you so much for such a nice presentation, Dr. Bea. It was a really pleasure to hear you speaking about all your work. We have already some questions from Carlos Larrea. He said, how much of CO2 that goes in is transformed into CO, or how much CO2 goes unreacted?
Yeah, okay, so the efficiency of these reactions is about 75 to 80%. So you'll have about 20% of CO2 in the output as well. So in the output, you will have, let's say, 80% CO and 20% CO2.
And he also asked if you separate these two gases in some way, or do you just liberate them both?
And does he mean in the outputs after the reaction?
Yeah, if you separate them afterwards.
It would depend on the application, depending on what the customer needs. If we do, it's a very simple pressure swing adsorption separation is well known in the industry. It's fairly easy to separate CO2 and CO, but it would depend on the application. There are certain applications that having some unreacted CO2 wouldn't matter.
Okay, thank you. We have more questions because you were explaining that when increasing scaling up these fuel cells, you have some issues. Which kind of problems are found in this process?
I think, one of the, quickest one for anybody that has done university research, and I think yesterday was also pointed it out, is, to scale up from sort of small devices into big devices, whether it's, grams of powder produced to bigger ceramics. The equipment, first of all, the equipment is a big deal because it's a very different kind of equipment and also a lot more expensive to scale up and to have equipment that can scale out processes. The number one is we needed to raise the funds to set up a lab, our own lab with bigger equipment than giant equipment. That is expensive. And so that was problem number one. Then to scale up, we solved a lot of the synthesis was fairly easy to scale up. The ceramics, in the screen printing, there are things that you got to be careful. It's not the same to screen print the electrode onto a small area into a bigger area, and also when you're the heat treatment as well. You need to be careful on, as the bigger you go, you need to be careful that you're not going to crack the ceramics and the rates going up and down, the cooling and heating rates of the ceramics. it's a little bit more tricky. And then if you go into the actual stack level, all the testing, the electrochemical testing out there is almost no options out there to buy commercially available test stations. You have to design it on your own, or hire engineering firms to design something for you. And as you can imagine, that's also not cheap. So those are one of the major, difficulties that we found, and we solved a lot of them by collaborating with industry, finding great partners, subcontract some of the work. There are things that we're not reinventing the wheel. Ceramics processing, lots of these processes are well known. We're not reinventing that. Not the microwave part. We're not dealing with the microwave, say on the commercial level. So I think those are, top of my head, the biggest issues. I would say funding is the number one.
Yeah, it's always the number one. We have one more question. Like, how many stacks are required per SeeO2 ton? Like, because you said you stack different fuel cells.
Yeah. So our bench prototype that we're testing today, that stack, it's one stack, and that can convert 4 tons of SeeO2 a year. That's per year, and that's a 1 kilowatt stack.
Okay, and that's a stack with 10 parallel.
It depends, but it's about between 10 and 16. Those are details that I'm not allowed to share.
Okay. So I'm not sure we have more questions. Well, I wanted to ask about the painting process that you use for the electrode on the electrolyte, like, because you have to make it symmetric. I guess it's not that easy as it may seem. Like, just
yes and no. So traditionally, when you're making these cells asymmetric, so when you have one material on one side and the other material on the other side, you would screen print one side, then heat treat it, high temperature, and then take it out and then paint the other side, and then heat treat it again, because the binding temperatures are different. But for us, it's actually a little bit easier, because you would paint one side and you would just let it dry, and then paint the other side, and then you can heat treat it once, because it's the same temperature that's needed to sinter both sides.
Okay, so I think we don't have any more questions. So thank you for your presentation, for answering the questions, and for the polar bear, which was so fun.
That's a picture that I took. Jesus doesn't let me share many pictures of my polar bears, so I just shared two, actually.
Oh, well, I think we have one more question. Is it possible at what current density do you run the electrolyzer step?
So I would answer it on the potential. So high temperature electrolyzers are ideally run on what's called a thermoneutral voltage, or thermoneutral potential. And that thermoneutral voltage, it's thermodynamically known. That's where, because they're endothermic reactions, and as I explained, you need external heat, that's the potential at which the internal heat generated by the resistance internally, it's equal to what is needed. So that's why it's called thermoneutral potential, so that they're run at that potential.
Okay. Okay, one last question. That's the last one, for sure, promise. Is the performance of the bigger cell equivalent to the one of the bottom cell? Like, but that's small and big.
Yes, generally, yes, that's correct.
Okay, so that's all. So thank you again.
Okay, thank you.